Hi everyone! Welcome to my video talking about the modes of inheritance and how to solve for them when you're looking at a pedigree. So in this video I'm going to be going through and filling in the chart that's titled Modes of Inheritance. We're going to be filling in the whole thing together, and this chart is going to be like your cheat sheet when you're solving pedigrees. Okay, if you know this chart, you should never ever get a pedigrees question wrong. So in your chart, looks like this. You have all of these titles already in there for you. We're going to be going through all of these different modes of inheritance. So we could have a trait that's found on the autosomal chromosomes. So for humans, that's pairs 1 to 22. And it could either be recessive or dominant. Okay, or we could have a trait that's found on the X chromosome, recessive or dominant, or on a Y chromosome. So we're going to go through what this looks like. Okay, all of our options. This first box, the top box, are going to be filling in all of the possible genotypes for the parents. Just kind of a little legend for yourself. And then we're going to be going through certain characteristics that you're going to be looking for in your pedigree chart that fits with each of our modes of inheritance. So, first of all, autosomal recessive, we'll move our way to the left as we go through the table. So, autosomal recessive, we know, is a recessive trait, so you have to have a little a to have it or be affected by it. If you have a big A, that means you do not have the trait. Okay? And a big A would be a carrier of the trait. They do not show it, but they carry it in their genetic code. So because we have carriers of this trait, if you mix two carriers together, you could potentially skip a generation, so the parents wouldn't have it, but all of a sudden their babies have it, which we say is skipping a generation. So it may skip a generation, which looks like this. Okay, two parents that are not affected, they're not shaded in, all of a sudden having a baby that is. That's what I look for when I'm looking at skipping a generation. Okay, we also know that if our parents are affected, if they both have the trait, they would both be little a. So all of their children would also have to be affected because they only have little a's to give off to their children. So all of their children would also be little a, and they would all be affected. So if I was looking at a pedigree like this, the family that I'm talking about would be all shaded in. Okay, if you all of a sudden had a baby that was not shaded in, you would know that autosomal recessive is not possible. Okay, now I say that it may skip a generation because that means that it can, but not every single time, every single pedigree, will it actually skip a generation. So I can say may skip a generation, but if it doesn't, that doesn't narrow it down for me. It still could possibly be autosomal recessive. This one though, if it does the opposite of skipping a generation, where we have two parents that are shaded in, and then all of a sudden having a non-shaded in baby, that means that it could not be autosomal recessive. It's not possible. So that is all of our tricks for autosomal recessive. Now we're going to move into autosomal dominant. So it's still an autosomal trait. So it looks like A's, big A, little a, and you have to have a big A to have this trait. If you do not have a big A, you are not affected by it, and there are no carriers. Because it's dominant, you can't be a carrier of the dominant. You either have the dominant or you don't. So there are no carriers, which also means that this trait is not going to skip a generation. So if you see it skipping a generation, you know that it's not autosomal dominant. Okay, it's not possible for two parents that do not have the trait. They would be little a if they do not have the trait. All of a sudden having a shaded in baby, then we're just all of a sudden getting that dominant trait out of nowhere. That's not possible. You'll also see with autosomal dominant having some baby that's shaded in only needing one parent. So we don't need both parents shaded in to have a baby that's shaded in. You only need one parent to be shaded in. So this parent could be big A or big A, and they could have some children that also have the big A, also being the dominant trait. So that's going to be something that we're looking for autosomal dominant. Now we're going to move into the X chromosomes. So it's carried on the X chromosomes. I have this separation in the middle of the top box because we're going to separate boys and girls. So starting with the males' genotypes, okay, we could either be unaffected if you have the big H. So X-linked recessive, an example that we talked about in class, was something like hemophilia or color blindness. those are both X-linked recessive traits. So a boy that does not have hemophilia would be big H. A boy that does have hemophilia would be little h. They're affected by the disorder. Girls, on the other hand, can be either homozygous dominant or heterozygous and not have the trait. To have the trait, they have to have 2 of the little letters, but they could also be a carrier. Again, they're unaffected, but they're carrying that small trait. So because we do have carriers, it is possible for this to skip a generation. So again, skipping a generation would look like this. The mother has to be the carrier, okay? And when she ends up going through and doing this, she could have a son that has the trait. Okay, you're also looking for some other tricks. For example, if you have a daughter that's shaded in, her father has to be shaded in. So it look like this. The daughter has it, the father has to have it. The daughter gets one of her X chromosomes from her father. Because her father only has one X, he would have to have a little h in order for her to inherit 2 little h's. Now, her mother would also have to be a carrier of that trait, but we're not going to be able to see that in an actual pedigree. So she is going to be a carrier, which we don't see in her shaded or not shaded in circle. But the father only has one little h, so he's going to show that he is affected, and his daughter also would be having 2 little h's. She would also be affected. So if the daughter has it, her father has to have it, okay, at the very least. Her mother could also have it, but we're looking for at least her father also being shaded in. Okay, another one is when I'm looking at the sons. If you see that a mother is affected, all of her sons have to have it. If the mother has 2 little h's on both of her X chromosomes, all of her sons are going to inherit because each of her sons gets one of her X chromosomes, and then the other son will get her other X chromosome. So if both of the X chromosomes carry a little h, there's no possibility for the son to get a different X chromosome. They get their Y chromosome from their dad. They're not getting any X chromosome from their dad. So if both of the X chromosomes from mom carry that little trait, all of her sons will have it. So it'll look like this. The mother has it, so both of her sons have it. And we also see the same trick that we saw in autosomal recessive, being that if 2 parents are affected, both mom and dad, all of their children are affected. Okay, it's because all of the X chromosomes that are possible to inherit carry that little H on it. So again, if you see 2 parents that are shaded in, and then all of a sudden one of their children are not shaded in, you know that it cannot possibly be X-linked recessive. So let's move on to X-linked dominant. So again, we're going to separate the boys and girls because they have different genotypes. Boys have to have a big H to be affected and a little h to be unaffected. Normally you would need 2 little h's to be unaffected, but boys only get 1 X chromosome. Girls, on the other hand, can be either homozygous dominant or heterozygous to be affected with the trait, or they are unaffected having the 2 little h's. And again, because this is a dominant trait, there are not carriers of it. If you have the dominant trait, you show that in your phenotype. So again, because there are no carriers, it cannot skip a generation. If you see it skipping a generation, you know that it cannot be the X-linked dominant or the autosomal dominant. Okay, we can cross out both of those as options. Okay, now when we're looking at other tricks to cross out X-linked dominant, they're going to be the opposite of these two. So if I'm looking at a father having it, all of his daughters have to have it, which looks like this. Okay, this is different because just because the daughter has it, her father having to have it, doesn't mean that all her sisters do. This one, all of the sisters will have it when the father has it. Okay, so it's a little bit different. All of the girls will have to be shaded in if the father has it. This one, if the father has it, okay, not all of his daughters have to be shaded in because we're working our way backwards. And the opposite of this, if I have a son that has it, his mother has to have it, but again, that doesn't mean that his brother does. So in this one, all of the boys were shaded in if the mom had it. This one, if the son has it, his mom has to be shaded in, but his brother doesn't necessarily have to be shaded in. So those are our tricks for X-linked dominant. These 4 are going to be the main ones. Okay, so when you're looking at actual pedigree questions, these are the 4 that you're going to see most often. Okay, but we also have the option of having a Y-linked trait. So I do want to show you what that looks like. Remember, Y-linked are only going to affect boys because only boys have Y chromosomes. So they would have a trait connected to their Y chromosome. It does not skip generations. If we end up not having any boys in our offspring, it's just gone from that family. Okay, the girls don't carry this trait because they don't have Y chromosomes. If a father has it, all of his sons will have it. He is passing on his Y chromosome to all of his sons, so you will see this trait staying in all of the sons. And girls cannot be affected with this disorder because they do not have a Y chromosome. So you will see a pedigree looking like this, where a father has it, all of his sons have it, and then all of his sons have it. All of a sudden we don't have any boys being born, so now it's completely gone from this family. If these girls have babies with someone, okay, their sons wouldn't have it because they can't pass on a Y chromosome to those sons. So that is our 5 different options. Remember, these 4 are our main ones. And I also have another trick for you guys to write down, but I just kind of ran out of room, so you guys can write this if you're running low on space as well. But if I look at the difference between autosomal and X-linked, boys are more likely to be affected with an X-linked trait because they only have to get 1 letter. So if you guys see a differentiation between boys and girls, okay, if you have like 5 girls affected and like 10 boys in the pedigree, it's probably going to be X-linked. So that's one of the first things that you're going to look at when you're solving an actual pedigree question. So that is the modes of inheritance chart that you guys need to know. You don't have to draw out on your drawing quiz tomorrow the actual little pedigrees that I have. I just wanted to show you guys what it would look like. You just have to remember the words. Okay, so if you guys want to practice writing out those words a couple times for your drawing quiz, that would probably be beneficial. But remember, you don't have to know the actual pedigree diagrams. Good luck studying tonight. You guys are going to kill it tomorrow. I will see you then.